All right. Sir Isaac Newton was born on Christmas Day in 1642. He lived a very long time, lived till 1727. He was an English physicist and mathematician. He also was one of those people that thought he knew everything. So he would have a hard time right now with the extra theories that have come about. For example, Newton's laws do not apply to your phone. Okay? You've got some theoretical physics going on in here. You have modern physics, quantum physics going on in your phone that do not fit in Newton's laws. He would struggle with that. Big time. He also would have struggled with a lot of ideas that Einstein had, because Einstein's special theories of relativity do not use any of Newton's laws. They don't fit. But at the time, and now, his laws are still applicable. You can still see them everywhere. It's just there's some places they don't fit. So much of our modern physics and chemistry ideas come from Newton. His three laws are the law of inertia, the law that deals with force, mass, and acceleration, and the law of equal and opposite forces. So, in a nutshell, Newton's first law says things keep moving or stay at rest until a net force acts upon them. So things continue to do what they were doing until something disturbs them. The second law says that a force causes acceleration while mass resists acceleration. How many of you have ever seen a big tractor-trailer truck try to stop in a small space? Doesn't work, does it? Okay. When they are driving and they are completely and fully loaded, it is not a good idea to try to turn in front of them or try to get in front of them when they're trying to stop, because they are bigger than you, which means they have a greater mass, which means that it takes a greater force to change their speed. So acceleration is defined as speeding up, slowing down, or changing direction. And so if something is bigger than you, you need to yield. Okay? Law 3 says for every action, there is an equal and opposite reaction. If you've ever fired a shotgun, you know this. If you've ever watched a rocket take off, or any other spacecraft take off, or if you've ever watched a jet fly off of an aircraft carrier, you know that the jet has to have a catapult to send it out. Okay? They have to add a lot of force to get it to go, but they also need something behind it for that force to bounce off of to propel it forward to get off the ship. So every action, there's an equal and opposite reaction. One of the things I'm always telling my students when they get angry is not to hit something. Because if you hit something, what's it going to do? According to Newton's third. If I hit something, it's going to hit me back. Okay? That's that pain you feel. All right? And depending on what you hit can depend on how much pain you have and if you break something. All right? So that's the first three laws. Well, there's actually more interpretation to them, but we'll get to that. So what is inertia? It is the property of an object that resists a change in motion. The main thing to know, the more mass something has, the more inertia it has. Think about the elephant and the mouse. Moving objects also have inertia. They want to keep moving. How many of you have ever been in a car and somebody forgot to put it in park? Yeah. What happens? Yeah. There's a reason why cars are called automobiles. Auto means self, mobile means motion. or driving. So you leave a car in park and the car's running, or even if it's turned off, if you're driving a stick shift, it's going to keep going. Okay. Objects at rest want to stay at rest. Okay. All the objects in this classroom that are staying where they are, they're going to stay where they are until something changes that. An earthquake, me picking them up, lots of different things. All right. Less mass, less inertia. So it makes sense. It's common sense, which is what's great about it, because with physics, you can totally see what's happening. All right, so that leads us to, well, what is a force? Well, a force is defined as a push or a pull. We use newtons as our unit of force. It's not an accident, okay? When you discover something in science, you get to name it, and he named it after himself. He was a little bit self-centered. Actually, he was a lot self-centered. So what is net force? Well, net force is the sum of all forces, and it has a direction. So the way you think about this is you think back to algebra, and some of you are like, do I have to? And you think about the number line. So we'll say that's 0. All numbers to the right of 0 are what? Positive or negative? Positive. So anything going to the east, okay, is going to be positive. Numbers to the left of 0 are what? Positive or negative? Negative, okay? And so if you have an object and you have two things applying a force to them, which one is going to win? Well, the one that has the greater force. So in this case, when we look at negative numbers, don't think of it as a bad thing. Think of it as a directional thing. Okay? So you add the two together. So you have 200 newtons minus 400 newtons. The net force is 200 newtons to the left. That makes sense? Actually, not hard. All right, we'll get more into the math of this tomorrow. But Newton's second law of motion says that there's a relationship between force, mass, and acceleration. It says that the bigger the force, the more acceleration it takes to change the direction of the force. The bigger the mass, the greater the force it takes to change the speed or the acceleration. And the bigger the acceleration, the more force you need to change it, to slow it down. Okay, so in the driver's manual, some of you may be studying for your permit, there's a formula in there that tells you for every 10 miles per hour that you're going, you should allow how many feet between you and the car in front of you? No? 10. Okay. Now, if you're driving on I-49 in busy traffic, you know that is not going to happen. You are not going to have 750 feet between you and the car in front of you. It's not going to happen. Okay. But that is what's considered a safe distance because of Newton's second law. So law enforcement officers use Newton's laws all the time. Anytime they have to work a car accident, they use those things, and they can calculate how fast vehicles are going using Newton's laws. Knowing what the conditions of the road are, looking at the tires, looking at skid marks, they can measure things. And so This is one of those things where students are like, how am I going to use this? Well, this is everywhere. Anytime you're driving or you're in a vehicle with somebody, this is here. Okay, it applies everywhere. So force equals ma says for the same acceleration, more mass means more force. You got to apply the brake more. Okay. Some cars have a panic brake. They're starting to take those out of cars now. My car doesn't have one. I have a parking brake, but it's not a panic brake anymore. For some mass, more acceleration requires more force. So big thing versus little thing, big thing is going to need more force to change its motion. Newton's second law says that when you stomp on the gas or hit your brakes, you use more force and wear out the engine parts and the brakes faster. That makes sense. All right. So like I said, we're going to get to the math of this. It'll be tomorrow. I'll probably do a couple of videos on how to solve some of these. You'll have some practice to do. But for now, what I